Greetings everybody, and welcome to our second video on vectors. So what we have in this problem is that a 50-pound weight is hung by a cable so that the left and right portions of the cable make an angle of 40 degrees and 53 degrees respectively with the horizontal. What we're asked to do then is to find the magnitude in pounds of the force of the tension in the right portion of the cable if the resultant force acting on the object is 0. So the resultant meaning that the object is not moving, so everything is stationary, and all forces, vertical and horizontal, are then balanced. So one thing that we need to do probably before we really dive into this problem is to talk about how you can come up with the components of a vector when just given some information about that vector. So suppose that you're given a vector v, and that what you know about that vector v is that you happen to know what the magnitude of v is, and you also know what the direction angle of that vector is going to be. And theta being the direction angle really just means that it's going to be the angle between, really I guess if we wanted to think about the unit vector I, so the unit vector in the positive x direction, so the unit vector in the positive x direction, then the direction angle is really just the angle between, is going to be the angle between our vector v and our vector I. And so that's going to be our direction angle. Well, if we have that direction angle, then the v we can actually write as the components being the length of v times the cosine of the direction angle in the I direction, and then the length of v times the sine of the direction angle in the j direction. And kind of really just doing that, if we kind of stop to think about, well, why is that going to be true? Well, it comes back down to our Pythagorean theorem and right triangles and back to trigonometry. So if I've got v sub x being the horizontal value and v sub y being the vertical value, then how do I get the components or the endpoints of that of that vector? They're just going to be v sub y, just going to be given by the length of v times the cosine of my direction angle and the length of v times my sine of my direction angle. So with that in hand, let's take a look at how we can understand this particular problem now. All right, so if we just kind of start labeling some vectors, well, we've got one vector, definitely that's going to be pretty obvious in this setting, and that's going to be our force of gravity. And one thing that we know about that force of gravity, it's going to be really just 50 pounds in the down direction. So if I were kind of labeling these things, that would be a minus 50 times our unit vector j in. So now our other two vectors that we're going to have in this problem, we've got a tension T1, or T2 rather, let's make T2 on that side, and a tension T1 on the left-hand side. So these are the forces in the rope that are pulling up on the weight as gravity is then pulling down. Now we know that these things are going to be the resultant force acting on the object is 0, which means that the sum of the forces, so the sum of the forces is really just going to be 0. So what we have then is that T1 plus T2 plus our force of gravity is going to give us 0. All right, so how can we write down now what these values are actually going to be? Well, for T1, what we know is that it makes an angle of 40 degrees, that we have an angle of 40 degrees with the horizontal. Well, if I kind of translate that down, what do I have then really kind of for a direction angle for my vector T1? Well, just kind of by good old geometry, if the angle on top is 40 degrees, that tells me that this angle is also going to be 40 degrees. And so what would my direction angle be? Well, it's going to just be 180 minus 40, so I get a value of 140 degrees. So now, kind of using what we just had, we can say that our T1 is going to be, well, whatever our magnitude of T1 is, times the cosine of 140 degrees in the I direction. And it's going to be the magnitude of T1 times the sine of 140 degrees in the J direction. Okay, and we can kind of do the same thing now for T2. In our right rope, we're going to have T2 being the magnitude of T2 times the cosine of 53 degrees in the I direction, plus the magnitude of T2 times the sine of 53 degrees in the J direction. Now, it's the magnitudes T1 and T2 that we really want to know about in this case. And then kind of for our final vector, we have our force of gravity, which is just going to be a minus 50 in the J direction. So now kind of putting these things together with the fact that the sum of our forces, T1 plus T2 plus our force of gravity, is going to be 0, what we then have is really something that looks like, when we kind of combine those terms, is that our magnitude T1 times the cosine of 140 degrees plus the magnitude T2 times the cosine of 53 degrees in the I direction, plus, then for our J direction, we've got our magnitude of T1. So I got our magnitude T1 times the sine of 140 degrees plus the magnitude of T2 times the sine of 53 degrees plus minus 50, and all of that in the J direction. And so adding these together then gives us what will be the 0 vector. Now, this in turn gives us something that we can then write as a system of equations. And that system really being the first part, well, how is a vector going to be 0? It's going to be of 0 when the first component is going to be equal to 0, and it's going to be equal to 0 when the second component is going to be 0. And so with that, we are then able to write down a system of equations that will involve the magnitude T1 and the magnitude T2. So setting our first component equal to 0, we have the magnitude of T1 times the cosine of 140 plus the magnitude of T2 times the cosine of 53 degrees gives us something that's going to be equal to 0. Then for our second equation, we have the magnitude of T1 times the sine of 140 plus the magnitude of T2 times the sine of 53 degrees minus 50 is going to give us 0. So now basically we need to solve this system of equations. So if I take that first equation, and I can kind of easily solve for one of the values. So for that one, I can really say that the magnitude of T1 then is going to be equal to the negative of the cosine of 53 degrees divided by the cosine of 140 degrees times the magnitude of T2. And in solving that one, I can then take the magnitude of T1 and I can substitute in to my second equation. So if I do that, what I then have is something that looks like negative the cosine of 53 degrees over the cosine of 140 times the sine of 140 is going to be times the magnitude of T2 is going to be, or plus the magnitude of T2 times the sine of 53 degrees is going to be equal to 50. So now what I can do is to factor out a sine of T2 in each one of those equations. Then I have an expression that looks something like this. And what we can do here to kind of maybe clean this up a little bit is to multiply both sides by our cosine of 140 degrees. And what that will then give us is then going to give us an equation that looks like the magnitude of T2 times the negative sine of 140 times the cosine of 53 plus the cosine of 140 times the sine of 53 degrees is equal to 50 times the cosine of 140 degrees. Well, we could actually use our trig identity to put those together because that actually looks like the cosine or one of our sum formulas for sine. So that using our trig identity, that then looks like the magnitude of T2 times the sine of the difference between 53 degrees and 140 degrees, and that's going to be equal to 50 times our cosine of 140. And so that's going to give us a value for the magnitude of T2 being 50 times the cosine of 140 divided by the sine of negative 87. So what we then have for that approximately, it will be 38.354,786.06. And the units that we had were pounds of force. So now that we know the magnitude of the tension on one side, we can go back to our system of equations and find the magnitude for the tension on the other side. So then from our first equation, we knew that the magnitude of T1 was going to be the negative cosine of 53 degrees over the cosine of 140 times the magnitude of T2. Well, plugging in the value that we just found out, or approximated for T2, we then have, for our approximating the tension in T1, we're going to have a value of 30.13204608 pounds of force. And so I hope you've enjoyed this application of vectors. We were able to find the tension in both of those ropes, and I will see you guys in the next example.